Hello students, myself Raki, Assistant Professor in the Department of Electronics and Communication Engineering in ABS Engineering College Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University Lucknow. Under the lecture series of Microwave and Radar Engineering and heading of Transmission Line, in the last lecture we have discussed with the equations of the transmission line, and today we will study about the solution of that equation. So, get started now. As per the two different types of transmission line equation we have derived in the last lecture, and in this lecture I am just writing the two of that, the two common transmission line equation. First one is the d square voltage V upon dz square should equal to gamma square V. This is the expression of the transmission line equation in the terms of voltage, and gamma here is the propagation constant. Gamma is the propagation constant. The second transmission line equation is in the terms of a current d square I upon dz square is equal to gamma square I, and again this gamma is in the propagation constant. The gamma is basically given by the under root z into y, and it is equal to alpha plus j beta, where alpha is our attenuation constant and beta is our phase constant. One of the now, as we have already discussed that today we will discuss about the solution of the transmission line equation. So, the first solution of the first equation, that is d square V upon dz square equal to gamma square V, should be equal to V equal to V plus e to the power minus gamma z plus V minus e to the power plus gamma z. The basically E plus and E minus are basically the directions of the wave. Direction in the from the sending end to the receiving end, and the direction from the receiving end towards the sending end, that is the V minus. And when we expand, and in the next expression just we have expanded the value of gamma, gamma is equal to alpha plus j beta, and it is expanded here, that is why the equation changes into V plus e to the power minus gamma z e to the power minus j beta z. And similarly here also, when we replace gamma with alpha plus j beta, the equation we will have is V minus e to the power plus gamma z e to the power j beta z. Now, beta z is what? Beta z is our electrical length of the transmission line, and it is given in the terms of and measured in the terms of radian. Now, the first equation which we have derived, that is in the terms of a voltage. Now, the transmission line equation is also expressed in the terms of current. So, the possible solution of this equation in the terms of is given by I equal to y naught under bracket V plus e to the power minus gamma z minus e to the power V minus e to the power gamma z, and again when we replace gamma with the alpha plus j beta, we are having with the expression y naught under bracket V plus e to the power minus gamma z e to the power minus j beta z minus V minus e to the power alpha z and e to the power j beta z. Again V plus and V minus are basically defines the direction of the wave, that is from the sending end to the receiving end and from the receiving end to the sending end. Now, the characteristic impedance, which is our Z naught, it can be derived from the above equation, and it is basically equal to 1 upon y naught, and that is equivalent to under root z upon y. So, the equation changes into r plus j omega L and g plus j omega C, and when we write it is in the terms of real and imaginary, that is R, which is a totally resistive load, and it is the X naught which combines both the capacitance and the inductive load. So, this is the characteristic impedance of the line, and we will deal with the importance of the characteristic impedance further also, but right now I just want to mention one particular line. The characteristic impedance of a transmission line plays the very important role in the transmission line, because whenever we know we say that the impedance is matched and we are not experiencing any reflecting wave here. In that case, impedance is only said to be matched when the input impedance is equivalent to the and the load impedance is equivalent to the characteristic impedance. In that case, the system is said to be matched, and in that case we are not experiencing any reflected wave. So, before going through more detail about the characteristic impedance, back to the lecture again. At microwave frequency, we know that R is very less than omega L. The reason behind this is omega is our 2 pi f, and whenever we say about the microwave frequency, we already know that it is a frequency in the gigahertz range. That is why R, which is independent of our frequency, should always be very less than omega L, because for any particular value of inductance, when we multiply that with such a higher range of frequency, that means its value increases. Similarly, G should be very less than omega C. Again the same reason, omega is equal to 2 pi f and the frequency is in gigahertz range. So, its value when we say omega C, it is very higher than G. G is our conductance and G is always inverse of the resistance. So, these are the assumption which we take before proceeding to further, that R should be very less than omega L and G should be very less than omega C. Now, based on this experience, when we write about the propagation constant, which is given by under root R plus j omega L multiplied with G plus j omega C, and when we multiply this equation, when we take this equation and just we are taking j omega from both this side, this one and this one common, then this will become omega j omega square, and we are also taking L and C common. So, this will be here. Now, what will the change in the expression then? 1 j omega L multiplied divided by the j omega L. So, this expression will be equal to 1 and this will be R upon j omega L. And when we divide this expression, because we have already multiplied the complete equation with the under root j omega square L C. So, we have to divide that also with j omega square L C under root. So, the first expression will be divided by j omega L and this expression will be divided by j omega C. When divided by j omega L 1, and when this is divided by j omega L, R upon j omega L. Similarly, here j omega C divided by j omega C, resultant will be 1, and G divided by j omega C, resultant will be G upon j omega C. Now, j omega square, so this can be written as j omega under root L C, and now when we multiply, we have 1 then we have 1 first, then 1 plus R upon j omega L plus G upon j omega C, and everything is to the power half. So, the next step is that we should have the binomial expansion of that, and when we take the binomial expansion and we just take the initial values, because higher order terms on the higher and when the frequency is on the denominator get cancelled. That is why we have taken the only the initial terms, because higher order terms frequency power keeps on increasing, and for in that case when the frequency is on the higher side and it is on the denominator, that means it does not contribute further and it get cancelled out. It should be have a very minimum value. That is why the approximate value sign is also initiated at the starting. So, by the binomial expansion, when we take the binomial expansion of this and we take just the initial terms, because the higher order terms get cancelled, because it is for we are calculating it for the higher frequency in the gigahertz range. So, 1 plus half r upon j omega l plus g upon j omega c. So, the next step will be equal to half when we multiplied the complete expression. So, j omega under root L C plus half r upon j omega and j omega get cancelled, r L and it is multiplied with the L C also. So, we are having the expression like this, and similarly when we multiplied the next expression also, half g upon j omega get cancelled, g by c and it is multiplied with L C also. So, the resultant which we get is this one, half r under root c upon L, because this L when get cancelled we are having the under root L here, c upon under root L, and similarly this c and this c cancel, we have a under root c here. So, L upon under root c, this or this is on the real side, and on the imaginary side we have only this j omega L C. And already we know when we write about the gamma, that is our propagation constant, gamma is equal to j alpha plus j beta. So, alpha is of the imaginary term, alpha is the real term and beta is our imaginary term. So, alpha will be this term, that is equal to half under bracket r under root c upon L plus g under root L upon c bracket close. This is our attenuation constant, and similarly our beta, that is our phase constant, basically is our imaginary term. So, this will be equal to this one, omega under root L C. Similarly, now we are going to calculate the characteristic impedance, and the characteristic impedance is given by Z naught is equal to under root r plus j omega L upon g plus j omega c. Again the same thing, first of all we have to divide this expression with j omega L and this expression with j omega c. So, what we are having here, we have to when we divide this, of course we multiplied also. So, we are getting with under root L upon c, this is multiplied j omega L 1 r upon j omega L, and then when we divide this one to the power half, that means under root, and we divide this expression with j omega c. So, we have 1 plus g upon j omega c, it is on the denominator. So, here we have minus half, and again by binomial expansion the same thing which we have done for the propagation constant can be repeated here, that first of all we do the complete binomial expansion of this, but since denominator carries the frequency, so the higher order terms will be very less in value as compared to the initial order terms. That is why we have just taken the initial order terms of the binomial expansion and discarded the higher order terms, and when we take just the initial term, so in that case we have the approximate values and it is given by under root L C and 1 plus half r upon j omega L, 1 minus half g upon j omega c. Now, the next one is under root L upon c, 1 plus when we take multiply the expansion, it is equal to of course under root L c 1 plus half r upon j omega L minus half upon g divided by j omega c, and when we multiplied this term and this term, what is going to happen? This will be 1 by 4 r g j square omega square L c. When the omega square term come, again we are saying that omega is in the gigahertz range, and since it is a very small value, since its omega comes on the denominator side, so this term will be discarded and we are have the only this term under root L by c 1 plus half r upon j omega L minus g upon j omega c. Now, so till now we have calculated, this is our characteristic impedance expression, and you have to remember this expression also, and initially we have calculated the attenuation constant as well as phase constant, and this you have to remember this value because these values are required in solving the numericals also. Now, the phase velocity, as we all know that the phase velocity is given by omega upon beta. So, what is omega? We have already seen here that beta is equal to omega into under root L c. So, omega upon omega under root L c. So, what we are having? We have left with the phase velocity that is equal to 1 upon under root L c. So, what we are having from this expression, that the product of L c is independent of the size and the separation of the conductors and depends upon only two values, that is permeability that is given by mu and the permittivity that is given by epsilon of the insulating material. So, when we talk about the lossless medium, normally mu is given by mu naught into mu r, and epsilon is given by epsilon naught epsilon r, where mu r is the relative permeability and epsilon r is the relative permittivity. So, this depends upon the material which we are using for the conduction process, but for this free space we already know that this mu r is equal to 1 and this epsilon r is also equal to 1. In that case, our phase velocity will be equal to 1 upon under root L c, and it is equal to, when we write the in the terms of permeability and the permittivity, this is given by 1 upon under root mu naught epsilon naught, and when we substitute with the value of the mu naught or epsilon naught, which you already discussed in the various lectures and you already know, in that case you obtain the value of the phase velocity equal to the velocity of light, that is equal to 3 into 10 to the power 8 millimeter per second. So, try to solve this by substituting the value of mu naught and epsilon naught, that you are getting the value equal to 3 into 10 to the power of 8 meter per second or not. Take it as an assignment for you. And now, when we are having the value of when we are taking any transmission line, a lossy transmission line, in that case what is going to happen? Our velocity will be equal to under root mu epsilon, and we know that this is mu naught mu r epsilon naught epsilon r, and when we break it down, mu naught epsilon naught mu r epsilon r, and we already know that 1 upon under root mu naught epsilon naught is equal to c. So, what we are getting here? This is the phase velocity when there is a lossy medium, and accordingly we can have the way we are able to calculate the velocity factor and the velocity factor is given by actual phase velocity upon the velocity of light in a vacuum. So, what will the actual velocity? Because any medium, there is no medium which is lossless. In practical condition, always we used to say that there always a medium which is the lossy, but in the 100% lossless medium does not exist practically. So, first here we are calculating the velocity factor, which is equal to the actual phase velocity upon velocity of light in vacuum, which is given by VE upon C. So, what is a V? V is equal to C upon under root mu r epsilon r, and it divided by C. Again I am writing V is equal to C upon under root mu r epsilon r, and it is divided by C. So, the C get cancelled and we are having the velocity factor as 1 upon under root mu r epsilon r. This is our velocity factor. Now, let us do one numerical related to the transmission line. There is one transmission line where it is what is given here, that r is equal to 2 omega per meter and g is equal to 0.5 millimho per meter, and the frequency is equal to 1 gigahertz, and you have to calculate the characteristic impedance and the propagation constant. So, before proceeding toward this numerical, first of all just have a look at the characteristic impedance and the propagation constant formula. So, first of all we will have the characteristic impedance formula. So, this is the formula of the characteristic impedance. So, substituting the values, what we are having, already we know by substituting the values we are having with these expressions, and when we know that for solving the expression from this angle form to the coordinate form, we already know that angle is 8.40 and 181.39 is the length here. So, when we say that we have to find out the real part and the imaginary part, so real part is on this side and the imaginary on this side. And the real part. So, the real part will be basically what we say, real part will be 181.39 cos of 8.40 and the imaginary part will be 181.39 sine of 8.40 degree. So, this is a process of solving the phasor diagram, angle and magnitude diagram with the real and the imaginary component. Similarly, for calculating the propagation constant, we just have the value of formula of the propagation constant. We have to substitute the values of r and everything which is required here, and when we solve it, again we get the result in the form of a phasor, and then we have to solve it in the terms of a imaginary and the real part. Similarly, by using the same process, that is, and here the angle is 158.63 degree and the distance is when we solve, you get the expression. So, always try that that you should write the answer in the terms of the real and the imaginary part, not in the form of a angle. But even if you write the answer in the form of angle, you will get mark, but it is better to write in the form of a real and the imaginary component. So, in this particular lecture, what we have studied, just have a review. We have gone through the expressions, solution expressions of the transmission line equation. Then we have discussed about the propagation constant, and its then at final we have calculated the attenuation constant and the propagation constant, phase constant, and at the end we have calculated the characteristic impedance also and do the numerical related to that. Also we have concluded that phase velocity for this free space should be equal to the velocity of light. So, thank you for attending today's lecture.